let's do this first. Let's look at this. We're gonna do a function. Yeah. It's a function where we plug in values of x and we get out y values. And it looks something like this. You could probably guess what this thing is. It's a function where when I plug in a 1 as my input, I get out a 1. When I plug in a 2, I get out a 4. Can you guess what function this is?
X. What?
Oh, I'm talking to myself. I'm sorry. What's your guess that this is?
Wow.
It's called a parabola.
Okay.
Any guesses? I'm gonna give it away. Here's the big giveaway. X squared.
Yeah. Okay.
We take an input value and we square it, and we get out this. That's why it shoots up like that, right? Because when you plug in a 2, you get out a 4, which is big. You plug in a 3, you get out a 9, which is big. You plug in a 4, you get out a 16, right? It shoots up real fast. What happens when I plug in a -1? What do I get out when I plug in a -1?
A 2. I mean a 1. Sorry.
Right. F of -1 is -1 squared, and a negative times a negative is a positive. And so we end up with a +1. What about when I plug in a -2? What do I get?
A 4.
A +4, right? So I plug in my -2 and I get out a +4. Okay, then. Another way, and I want to do this real quick. We're going to remember our one way that we used to think about functions here is we have something like this. There's another way of representing or thinking about a function is we could say, well, it's a map that maps a domain into a range, right? And this guy is going to go, oh, I don't know, -4, -3, -2, -1, 0, 1, 2, 3, 4, and so on. And this function is the rule which says, okay, 0 gets mapped to 0. You already told me that 1 goes to 1. 2 squared is 4, right? And so on and so forth. And -1 squared is what?
1.
+1. And -2 squared is what?
4.
+4. Okay. All right. It looks a little jumbled, but you get the idea here. Now, if we want to think about the inverse of this, so remember, inverse is you took your function and you put something into it, and out popped a, let's say, out popped a 4. What was your input? If your output was a 4, what was your input?
2 or -2?
2 or -2, right? Because you're saying, well, you plug something into here and you got out a 4. There's only 2 possibilities. Either you plugged in a 2 or you plugged in a -2, and that's where it came from. But if you remember the definition of a function, right, is that every one input goes to one output. So now when we're considering the inverse of this as a function, it's like saying, well, any one input that you give it, right? Like now we're thinking about the outputs as inputs, right? We're doing the opposite game, right? We're saying, if we want to go backwards, now we no longer have a function, because with one input here, to go back, we have 2 places it could have come from. So the inverse of this is not a function. We're kind of in a bind here because we only want to deal with functions. And that kind of makes sense, right? if I have some function g and I plug in a 4, it's not going to do me much good to say, well, it might be a 2 or it might be a -2. Like, that's not what a function is, right? So this is what we do in this case. We're going to say, well, you know what? We want to be able to undo squared, right? Like this function right here. It takes something and squares it. And we would like a function which tells me where it came from. But we have this problem that half of the numbers here, all of these numbers, are hitting the same numbers that already get hit by all of these numbers. So what we're going to do is for now just restrict this guy and say, you know what? If we just consider this, if we forget about all the negatives that there were, then we have a perfectly good function. As a matter of fact, it even looks nice here. We could say, you know what? When we're dealing with the inverse of squared, so in other words, you took something and squared it and got out a 4. What we're going to do is say, yes, we understand that it might have been a -2 as well. But for right now, because we want to define this new function or this new operation, which we're going to call square root, go figure, we're going to say, forget about the negatives. For right now, we are not going to consider negatives. And so that's exactly what we're going to do. We're going to say, okay, then we have a new function, g, and we call it square root. And it's the thing that just undoes this right here. So in fact, since we called these x's and we called these guys y's here, I'm going to go ahead and think about this as my inputs are my inputs to the new function are the outputs of the old function. That makes sense. In other words, we have some function that we're very familiar with, which is x squared. You take a number and multiply it by itself. And this is what it does, right? You plug in a 2, gets out a 4. Now we want to have a new function which says you did that, right? You plugged in some number and you got out a 4. Where did it come from? Well, we call that a square root. And so we say just kind of by definition here, the square root of 4 is 2. This should not be new to you, this whole square root of something, right? That's not new, is it?
No.
No. Okay. So right now I'm saying I wanted to go over this because it connects functions back into, or it brings us back into talking about functions. Also, graphing is a really nice way to visualize all of this stuff. But this is what this means, right? So, but we have defined this is what we call the principal square root, which is what we get when we say, you know what, screw all of those negative inputs to that original squared function. We're just going to deal with the positives right now. So whenever we have a number that we plug into here, we're going to know that you're talking about the positive one. But if we had, so just as an aside here, if we had an equation like this, and then we said, solve that equation, yes, we could factor it out and do like what we've been doing. Or we could say, well, x squared equals 4, right? Because I just add 4 to both sides. And then we could say, well, if you take the square root of that, right? We take the square root of both sides, we would have x equals 2, because 2 is the square root of 4. But we'd have to know, like, wait a second, like in this context, we're solving an equation. And there's more than one answer here. Like when I look at this, x squared equals 4, in that case, we're talking about the big picture here. We're saying, well, wait a second, like in the context of an equation, we have to be careful. But what we're going to start doing, and so this will come back into play later, where we're going to have to consider, wait a second, there are 2 answers to this equation. Both +2 and -2 solve this equation. So we need to worry about that when we are actually working with equations and solving square roots, solving using roots and stuff like that. But right now, we're going to forget about all of that stuff and we're just going to consider the positive one. Yeah, of course that happened. Of course that happened. So let's get this back. All right, there we go. Okay, so you following so far?
Yeah.
Okay, so let's talk a little bit about this. Well, actually, there's one more thing I want to do. So talking about the principal square root, we're talking about the positive one where we've said, okay, we're just going to pretend that this game was, we plugged in only positive numbers. And of course, we're only going to get out positive numbers when you square something. And so when we pull it back, right, when we plug in our old output, we get the positive one. We understand that there's also a negative one that's true, but we're just, whenever you see this sign, it's called a radical. Whenever you see this radical, we understand that what we're talking about is just the positive place that it came from. Okay. Now, here's something a little bit different. X cubed. Let's think about what x cubed looks like if we were to graph this bad boy. So let's just plug in a few inputs here. We have 1, 2, and 3. And how about -1, -2, and -3? So what's 1 cubed?
Sorry.
Take your time.
Okay, 1 cubed is 1.
1 cubed is 1 because 1 times 1 times 1 comes out to be a big fat positive 1. What about 2 cubed? I plug in a 2 into here and I have 2 cubed. That gives me what?
Eight.
Yes, because 2 cubed is 2 times 2 times 2, which is 4 times 2 is 8. And so we plug in a 2, we get out an 8. This is not going to be drawn to scale, but it will be qualitatively accurate. What about 3 cubed?
Okay.
Yeah.
27.
Yeah, 27, because 9, 3 times 3, and then one more 3 would give me 27. So it goes way up here, but it's not going to look like it's way up there. But you get the idea. It's up here at positive 27. Now, what about -1 cubed? What is that guy?
Oh, geez. Hold on. So, -1.
It is -1 because you got the negatives here. And remember, we talked about this before, right? We had an odd number of negatives. And so all of the evens pair off to give you a positive. And then you always have one dude left over who's negative, and it gives you a -1. So I'm going to plug him down here. And we end up with -1 as an output. What about -2 cubed?
That would be -8.
-8. And again, it's the same reason. We have an odd number of negatives. So all the evens pair off to give you a positive. And then you have one negative left over. A positive 4 times a -2 is a -8. And so I'm going to put him down here as -8. Okay. Now what about -3 cubed?
That would be -27.
-27. He comes down here and we get a -27. So now we have the overall shape of what this thing looks like. Kind of looks like a parabola to start off, right? It does something that shoots up real fast like that. And it shoots up faster than a parabola because it's going up way fast. And it kind of shoots down this way. In fact, it's kind of the reflection of this. If you reflected it and then flipped it over that way, you would have the same thing. Now, here's the interesting thing here. So we have negative, let's just do -2, -1, 0, 1, and 2. Those are going to get mapped to, let's do it this way, -8, -4, how about 0, +4, +8, and so on and so forth. The cool thing about this, well, 0, what's 0 cubed?
0.
0, right? Okay. 1, oh, I didn't put 1 in here. Okay, give me just a second. Sorry about this. We're going to go 1, 4, 8, and so on. 1, 4, 8, and so on. Okay, -1 got mapped to -1. 1 got mapped to +1. 2 got mapped to +8. -2 got mapped to -8. And now we don't have this problem where you're getting multiple inputs going to one output. Like in the case of x squared, we had both 2 and -2 getting mapped to 4. And so when we played the inverse game, right, and said, okay, 4 is your output, what was your input? It was ambiguous because it could have either been -2 or it could have been +2. In this case, there's no ambiguity. If your output is +8, there's no way it came from -2, because the only way to get 8 as an output is if it came from +2. When your output is -27, you know that it must have come from a negative number. And so you know it must be the root here, which would be 3, -3, and so on and so forth. So when we go to define an inverse function for this guy, it looks almost exactly the same, but now instead of having nothing right there, we write a little 3, meaning it's the cube root, meaning that we're undoing this function right here. You took a number, you plugged it into this function, and out popped an 8. And so you know that, well, what cubed equals 8? 2 cubed is the same thing as 8. So your input must have been a 2. And so when we do that kind of thing, there's no ambiguity. So we don't need to chop that guy off. We don't need to talk about a principal cube root. Well, the same thing is true for a 5th root or a 7th root or a 9th root, right? Because anytime you have an odd number of things multiplied by each other, the sign stays the same, right? Like -1 to the 7th is equal to -1 because you have an odd number, right? The evens all pair off. You're left with one odd negative, and that comes out to be negative. So in the case of odd roots, yeah, right? Odd numbers can be written like this, 2k plus 1. Whenever you have an odd number root, then it's just whatever the root is. Like, we don't need to worry about this mixing of negatives and positives. But when you have an even number root, right, when it's 2, 4, 6, 8, 10, 12, and so on, then we have to worry about this thing. And we always have, and so we're always going to take the principal square root, which is the absolute value of whatever it could be. We're always going to take the positive. Does that make sense? So what I'm saying here with this would be a good thing to commit to memory right here, is whenever you have an odd root, the answer is either positive or negative. And it depends on if that guy's negative, right? Like if it's -27 and you're taking a cube root, you know it must have come from -3. If it's even, right? If it's an even number root, you're always taking the positive. Always, always, always taking the positive. Any questions as of right now?
No.
Okay, let's check for understanding here. So let's get rid of some of this stuff. And let's do this.
Oh.
So let's take the square root of 16 and let's do the cube root of 8 and do the square root of 4 and the cube root of, let's go -27. Okay, so here we go. What is the square root of 16?
4.
4. Why? Well, because 4 times 4, something times itself, is equal to 16. Okay, so then since that thing is 4, that's what that means. What about the cube root of 8?
2.
Yes, it is equal to 2. Why? Well, and here, I'm going to go ahead and do this. I'm going to say, the reason why this is true is because 16 is equal to 4 squared. If we think about the game that we were just playing, you took some number, plugged it into squared, right? You took a number and squared it, and out came 16. And now this says, undo what you just did, and we know we're going to take the positive one. So it says, you took a number and squared it, and out came 16. That's what this means. You took a number, squared it, and out came 16. What number must that have been? Understanding that we're taking the positive, well, it must have been 4. Why? Because 4 squared is 16. Same thing here. This says you took some number and cubed it and it got an 8. And what number was that? Well, it must have been 2 because 2 cubed is equal to 8. Square root of 4 is what?
Uh,
I think I heard you say it, but I think you cut out. What is it?
I didn't say anything.
Oh, you didn't? Oh, sorry. The square root of 4.
2.
2. Why?
Because 2 times itself is 4.
There we go. Because 2 squared, 2 times itself, is 4. Okay? What about this? The cube root of -27.
-9. No, it's not. Wait, -3.
-3. There you go. Why?
Because -3 cubed is. Sorry.
Is -27. These mean the same thing. This is a fancy way of writing this right here. And so in your homework, you're going to have a couple of questions that are going to say, it's going to give you something like this, and it's going to tell you to write it like this. Now, you'll notice here. Oh, yeah, let's go ahead and talk about that right now. So, what is this? What's the square root of a squared? And it might help you to convert it over here first and think about it. Let's do it this way. It's equal to something. We don't know what that is. That's what we want to fill out. But let's just by analogy here, let's look at this guy and think about what this would be. Since whatever goes in here is my output, right? You took something as an input and out popped an a squared.
Your camera went off.
Of course it did. There we go. It disconnected on me immediately. Oh man. Oh, this is frustrating. All right, you. All right, it doesn't look horrible. Okay, so here we go. So we're working on this right here. We have the square root of a squared equals something. And we said, well, we could, by analogy, do the same thing we did before and say, you took some number and squared it. You took some number and squared it and got a squared. What number must that be?
A.
A, right? And so we'd say, okay, it must have been, the answer here must be A. But wait a second. We have to consider the principal square root here, because that's what this means, right? We understand that we're not going to even worry about the negative one. Like, yes, -2 does fulfill this. It does make this true. But since what we're doing is only talking about the positive ones, this is actually the absolute value of A right there, because that is what this means. That's the game we're playing. We're only taking positive values. So while it's true that -2 squared does come out to be 4, we're never going to say that the principal square root of 4 is -2, because that's not how we've defined it. We've said, no, we're only taking positive values. And so in this case, right, we're only taking positive values. And so when you have the square root of something squared, it's the absolute value of whatever that thing is. So to be clear, if I had the square root of -13 squared, I would say, well, wait a second. The square root of something squared is just whatever it is. And I'd be tempted to say, oh, it's just -13. But by definition, this has to be a positive number. So we take the absolute value of that guy and say, aha, it must be +13, even though, yes, it's negative and stuff like that. By definition, whatever comes out of this guy, this is a function, right? It says, take the principal square root. You have to have a positive number right there. So to be even more clear, if I had something like this, the square, or to be even less clear, if I had -2x squared like that, I would have to say, well, the square root of something squared is just whatever it is. But it's the square root, or I'm sorry, it's the absolute value of whatever it is. So the absolute value of -2x. And then you could just say 2x, but we're going to leave it right there like that, because we don't know whether x is positive or negative. And that's kind of a pain, but it's just much easier to just say just the absolute value right there. It's the absolute value. Now, I just want to say later on, we're going to be using square roots to solve equations, in which case we're going to say, we need both answers. So when we take a square root in order to solve an equation, it's going to split into both a positive and a negative answer. But right now, for this section, we're only going to worry about taking the principal square root, which is the absolute value of whatever's in there. Now, a little bit more here. What if I had the cube root of b cubed? What is that going to equal?
B.
Just b. No worries about positives or negatives here, because it's an odd number root. And so whatever b cubed is, even if it's a negative number, that's perfectly fine. We don't have to worry about whether it's positive or negative. It's good to go. So if I have the cube root, actually, let's do this. We're going to make it even trickier. We're going to say the 17th root of -3 to the 17th power is what?
-3.
-3. There you go. Because what this says, right? Think about it this way. We could say you took some number, raised it to the 17th power, and out popped -3 to the 17th power. What number did you raise to the 17th power to get it? Well, it must have been -3, right? And so that's the relationship. This is a fancy way of writing this thing right here. And so with odd number roots, we don't have to worry about the sign. Whatever we see in there, it just preserves the sign. But an even number root, let's try this. -2, let's take the 6th root of -2 to the 6th. What is that equal to?
The little value of 2, right? Or whatever.
What did you say?
Hold on. Would it be 2?
It
with
is
the
positive.
value signs?
Yeah, and what we could do is technically, we could say, well, it's whatever's in there in absolute value. And so we'd say, yep, the absolute value of -2, which does come out to be 2. The tricky part comes when we have something like this. In that case, we can't just say, oh, it's 2a, because what if a itself is a negative number? Ah, that's ugly. And so when you have variables in there like this, we're going to say, you know what? We're just going to leave it like this. And as long as we put those absolute value bars, we don't have to worry about it. So with something like this, with an actual number, you could just go ahead and answer whatever that positive number is. But when you have variables in there, that might change things. And so it's much easier to just say, okay, you know what, we're just going to put absolute value bars on there so that we could be sure that we're taking the positive number that pops out. Because if a were a -1 and you said, oh, it's just 2a, well, then you'd have 2 times -1 is -2. And no, just put the absolute value bars. So does that make sense thus far?
Yeah, I think so.
Okay, cool. So yeah, and so here, this is in your book, and this is actually something I think and I wrote that actually, I wrote it down a little bit differently than how your book does it, but this is a good one. And it does it to the k, right? Yeah, okay, so we do it like this. The 2k plus 1 root of a to the 2k plus 1. So in other words, an odd number, or I'm sorry, a number raised to an odd power, and you take the same odd root, is just whatever that number is. An even root, right? A number raised to an even power with that even root is the absolute value of whatever that is. Okay, so that's a nice one to have in your head. Your book writes it a little bit differently, but since we've talked about even and odd numbers, I feel fairly confident that you could just look at that and in your head go, yep, that means odd. Yep, that means even. So, okay. We good to go for right now?
Yeah.
Okay, so there's one more thing we really need to talk about in terms of roots, and your book doesn't really talk about this. Turns out that the square root of a fraction, so the square root of a over b, is the exact same thing as the square root of a over the square root of b. For instance, whoa. Okay, so let's go 16 over 25. The square root of 16 over 25. Well, not going to use my brain yet. I'm just going to use this fact that the square root of a fraction is a fraction of the square roots. So I'm just going to say, okay, whatever's on top, I'm going to put in the square root sign. Whatever's in the bottom, I'm going to put in a square root sign like that. Okay, so what is this? What is the square root of 16?
4.
What's the square root of 25?
5.
There you go. So you're going to have some questions like that. It's going to say, find the square root of 81 over 144. And that's all it's asking for. You basically take the square root of the top, square root of the bottom, boom. If there's something to cancel out, go ahead and cancel it out. I don't think there's any like that in your homework, but that's the idea. And actually, what's more true than just this, it's not just square roots that this is true for. It's in fact any root. You have the nth root here. Notice it has nothing to do with positive or negative. Any number root, right? 4, 5, 6, 7, 8, 9, doesn't matter. It breaks up like this. So that's something you could always use. That's always true right there. Okay. So you have a bunch. It says find square roots of this. Find square roots of this. They'll have something like this. They'll say, what's the negative square root of 4? What's the negative square root of 4?
-2.
-2. And basically what they're doing here is they're saying, do this, right? Take the principal square root. Okay, so I took the principal square root. It turned out to be 2. And then they're saying it's just negative. We're just going to make it negative after all that. So there's not much going on there. It's just, you'll see that. I don't want that to come as a surprise when you see it. It's also decimals. I'm not going to go into decimals. You can figure that out for yourself. Yeah, and so we talked about that. We talked about that. All right. 1 second. Let me look at something. Yeah, so let's do this. Oh, and what I didn't state this explicitly. You probably know this though. If there's no number there, it's assumed to be a 2. Okay, so we're talking square root whenever you don't see anything. So it's the square root. If it's something else like a 3 or a 4 or a 5, it has to be shown. And so in this case, without a 2 there, you know that there's a 2 there. So what is this? Let's do an easier one. What is this?
A.
Is it A, or is there something we have to do because it's an even root?
The absolute value sign.
The absolute value of A. Okay. And so by analogy, then, what does this guy have to be?
The absolute value of 5 minus B.
There you go. There you go. Okay. That's exactly what that is. Now, what if it was that?
Just be 5 minus B.
Just plain old 5 minus B. Exactly. Plain old 5 minus B. No frills there. Okay. Almost done here. Almost done. So that's good. That's good. We got that. We got that. We did that. Yep, we did that. Now, real quick, let's solve an equation involving these guys. Okay, I have this equation right here. The square root of some number is equal to 4. What number must that be?
16.
It has to be 16, right? And in this case, it's an easy one because you know that one. You know that the square root of 16 is 4. You know that 4 times 4 is 16. So you could just say, yeah, x is 16. That's cool. But what else does this mean? Remember, we said that we could rewrite this in exponential form. How would I rewrite this in exponential form?
4 squared.
Equals what?
16.
Well, yeah, but what is that guy right there?
X.
There you go. Right. So this, in other words, what I'm saying is this. This means what?
X equals X, what, Y squared?
X equals Y squared, right? That is what that means. Okay. So if you're trying to solve an equation, let's say for X, what you would do, and this is how I think about it, is, well, you square both sides. Why is that? Well, because the square root of a number times itself is whatever that number is, right? That's like the definition of square root, right? Like if the square root of X is 4, then it times itself has got to come out to be whatever that thing squared is, just like you said, you knew ahead of time it was 16, right? But how did we get that? Well, if you, again, I'm just going to say it, square both sides, this is how you get that guy to come out, right? And so by analogy here, if we have the cube root of X equals Y, how do we get that X by itself? In other words, what is the corresponding the corresponding power equation here?
Oh, X equals Y cubed.
I believe it. Let's really convince ourselves of that. Let's find ones that we do know here. For instance, I know that the cubed root of 8 is 2, right? We've done that one a couple of times. Why is that the case? Well, because it turns out that 8 is equal to 2 cubed. And you see what's kind of playing the roles here, right? Like my input here is like 8, and they're both the things that come out when I undo this. In fact, like this is a fancy way of saying this right here. They mean the same thing, right? If I take 2, multiply it by itself 3 times, I get 8. And so it turns out that, whoa. It turns out, right, like if we're playing that game, you plugged in some number into X cubed and out popped an 8. What number was it? Well, it must have been 2. This is just a different way of writing the same thing. And so it follows that we could say, well, okay, you plugged in some number X and you got out a Y. Well, it must be the case that that number, or I'm sorry, you plugged in a number Y, cubed it, and got out an X. And now you said, well, where did it come from? Well, it must have come from here. So, oh boy, that guy is not happy. And so, what I'm getting at is that if you have an equation involving the nth root of some number, and you say that that's equal to some value, it's the exact same thing as saying that X is equal to that to the nth power. In fact, it is what it means. That's precisely what it means. You took a number, raised it to the nth power, and got out an x. Okay? So then we're saying x was your output, and now when you take the root of it, the nth root of it, where did it come from? Well, it must have come from y. And there's that relationship right there. And that's, what we're saying right here. When you take 2 and you cube it, you get out an 8. Therefore, if 8 was your output and you took the cube root, you would have ended up back at 2. And so these are just saying the same thing there. And this is how you would solve one of these equations if and when you encounter them. So if you had something like this, this way. Oh boy, yikes. What are we going to do about that? Well, what we've just been talking about for the last 5 minutes was a case where you had the square root of something is equal to something else. And so we're almost in that situation here. This says 2 times something is equal to that. And so if I could turn this thing into something like this, I'll know what to do, because I know that this means that z equals w squared, and I could get that z by itself. I'm trying to get x by itself here. And so what do I want to do to get that thing to look more like that thing?
Divide both sides by 2.
There you go, precisely. And it's really nice to be able to look at this and to remember this guy here is just a number. It's just, it tells me to do something. I'm going to take a square root, yeah, but it's a number. And so this means 2 times a number. The 2 is the thing that's screwing up my life. If I didn't have that 2 there, my life would be a lot better. And so in order to get rid of something times 2, I divide by 2. And now I'm left with the square root of x is equal to 8. 8 divided by 2 is 4. And so now what do we do? Yes, we know what the answer is, but let's go ahead and how do we turn this into an exponential equation?
You do the so the square root of, I guess, x equals 2.
X equals what? Look over here. How did we get out of here? We said that this is a fancy way of writing this.
Yeah, so that equals 2 squared.
Fancy
Right?
way of writing what?
Doesn't that equal 2 squared?
It equals 4 squared.
Wait, what?
Right? And this is what we've been talking about, right? The square root of a number equal to some other number means the same thing as x equals that number squared.
Oh, right.
You're going the wrong way.
I don't know what
You're doing the thing. You're trying to think about it. Don't think about it. Like, this is what it means to be a square root, is that when there's some number multiplied by itself and blah, 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 blah. What number is well, the way we undo square root is to square both sides. Right? That's what this means. So we have a square root is equal to something. The way we get rid of the square root is you just take both sides and square them. A square root times itself is equal to whatever that thing is. And so we have to square that side as well. And let's just check. So we found that x is equal to 16. Let's plug that back into my original equation and see if that works. We had 2 times the root x is equal to 8. So 2 times root 16, it says, is equal to 8. What's the square root of 16?
4.
Is 2 times 4 equal to 8?
Yeah.
Last time I checked, yeah, 8 equals 8. So I know what you're doing, right? Like you say, well, it's 2, right? Because the square root and you have 4 and you're squaring something. The thing you square to get 4 is 2. But you're thinking about that backwards, right? It's just like, wait. We got to square 4. That's the thing that goes in there, right? Because the square root of what is equal to 4? In other words, 4 times itself is equal to whatever that thing is, the inverse, right? So that's a very common when you first start working with these things, especially seeing them as equations.
Right.
That's what really messes you up, right? So you're gonna have a bunch of, well, actually not too many at the beginning. You're gonna have like 1 or 2 like that. But this is something we got to get our heads around. But the idea, and here, I think it'll be good to take just an extra couple minutes to talk about this right here. So let's take one that we know for certain. What's the square root of 4?
Two.
Yes. Square root of 4 is 2. And we say why? Because 2 squared is equal to 4, right? That's what we've been talking about. And now let's look at this. Okay. I'm telling you that this thing, this symbol right here, is equal to 2. In fact, you're telling me that. You just told me that this is equal to 2. In other words, and I'm just real quick, plug this guy in. That's because we plugged in a 2 to the function x squared. We squared 2 and we got out a 4. And so this is the thing that says you got out a 4. Where did it come from? Well, it came from 2. So this symbol right here means the same thing as 2. Okay, so if I wanted to write 2 times 2, I could just say, well, hold up, you just told me that 2 is equal to the square root of 4. Right? So instead of writing a 2, I could just write the square root of 4. And here I could just write the square root of 4. Right? 2 times 2 is the same thing as 2 squared. But we just said that 2 and the square root of 4 mean exactly the same thing. Right? So what did I'm messing with symbols here, right? I could have written a smiley face right here and replaced each one of these with a smiley face, but we started with something that kind of we could wrap our heads around, right? The square root of 4, whatever this thing means, it means 2. So this symbol means the same thing as 2. And I know that if I take that and multiply it by itself, well, since those are equal, it has to be the same thing when I take that and multiply it by itself. But when I multiply something by itself, we have a funky way of writing it. And it's just, we write whatever that thing is, and we write a little 2 to the top, just like that. But that is equal to 4, right? And so what did we just find? Square root of 4 squared. You take that thing and square it, and out pops the thing that's on the inside, right? You following this so far? Do you believe this?
Mm-hmm.
Okay, so since we believe that, let's go ahead and think about this. Let's say, and actually, let me go back to this picture. We have our function which says square your thing, right? And so I'm going to plug in an x. I square it. Actually, I'm not going to plug in an x. I'm going to plug in a y. I'm going to plug in a y and I'm going to square it. And I'm going to get an x. X is my output. So I'm imagining I took a 2, I squared it, and out popped a 4, right? And now we're going to say, okay, well, if that's true, then the square root of that thing that we got out, the square root of the output, is equal to the input, just by definition of what all this stuff means right here. Right? Took a number, squared it, out came that. Same thing here. You took a number, you took 2, squared it, out popped the 4. So that means that when you find out where it came from, you ended up at 2. So we're just starting with something that's true here. Well, then, okay, if I square both sides, let's think about that, right? We know that y times y, that's how we got x in the first place. Kind of like that's how you got 4 in the first place. You took that thing and you multiply it by itself, right? So I'm going to do that here. I'm going to take whatever's on the left-hand side, multiply it by itself. Well, that's how we got x. That should just be x, but let's just look at this and see what this says. Since y is equal to root x, I could say y times y is equal to root x times root x. And so I end up with a y squared and a square root of x squared, right? I'm just following the same reasoning here, but instead of having actual numbers, I'm just using letters, right? But wait a second, y squared was how I got x, right? That's what I did. I plugged in y into the function square, and therefore y times itself is equal to x. And so let's see what we end up with here. I take a square root and square it, and I get the thing that's inside of it. In other words, if I'm trying to get x by itself, and it's under a square root, I just take that thing and square it, and it makes it pop out. And that's kind of what's going on here, right? You have the square root of 4, whatever it happens to be. But I know that when I take that and square it, that makes whatever's inside pop out. That's how you get rid of a square root. And so this is really useful. I'm kind of going, you see it in the section because there is a homework problem on this stuff, but they don't really go over it explicitly. They go over it later in a later section, but I think it's good to go over it now. Do you see why this is, why like the parallels here and why this has to be true?
Yeah.
Yeah, it takes some messing around with, and it looks weird because now we have this weird symbol. But basically what I'm saying is, if the thing that you're trying to get to is this, right, the x, kind of like if you have an equation that says take 2 and multiply by x and you get 4, and it's like the thing I want to get by itself is x. How do I get rid of the other stuff? Well, the way to get x by itself in this case would be to divide by 2. But in this case, right, it's like if I have an equation with an x in it, and I have, oh, I don't know, like a 5. And it's like, well, how do I get the x by itself? The way to do it is to square both sides, because when you square that root right there, when you take it and undo it, basically, it brings it back to where it started. In other words, we say this right here, if I square this side and I square that side, they have to be the same. And so that is the thing. The whole reason I did that, it's kind of like, why did you divide by 2? Well, to get the x by itself. Why did I square that thing? To get the x by itself. This is x right there. And so we could say that x equals 5 squared. In other words, x equals 25. And we could check and say, wait, does this make sense? Yeah, the square root of 25 is 5. Yeah, that's how we do it. But when these things start to get really ugly, right? Like when it's like we could have just solved this in our heads and said the square root of something is 5. Oh, so 5, what's squared? Oh, 5 squared is 25. So 25 is the thing that goes in there. But when it's something like this, uh-oh, now I have to do a whole nother step, and I don't want to have to think about that. So I'm not going to think about it. I'm just going to say the way to get the inside stuff by itself is to square it. So I'm going to take it, square both sides. That makes the x plus 1 pop out. And we get 5 squared. X plus 1 is 5 squared is 25. Subtract the 1 from both sides, and I get x equals 24. And let's see if that makes sense. The square root of x plus 1, if x is 24, it's x equals 24, so 24 plus 1, which is the square root of 25. Yeah, the square root of 25 I know is 5. And yes, 5 and 5. And so that's the idea. This is a really nifty thing to do. And it's like, I want to get x by itself, but he's buried in a square root. What do I do? Well, to square a square root makes whatever's inside pop out. So, does that make sense?
Yes, I think so.
Okay. We'll return to that soon. So don't worry about that right now. The final thing we need to talk about is domain. It's dealing with square roots. So, and cubits and all kinds of roots. So back to our first picture, we had a parabola. Okay, and we said that this, actually we're going to call it G. I'm going to say G of x is x squared. And we saw that when you plug in a 1, you get out a 1. Same thing, you plug in a -1, you get out a 1. When you plug in a 2, you get out a 4. Plug in a -2, and you get out a +4. So then we went and defined a function and said, okay, you know what? We're going to have the square root function to be talking about when you take one of these numbers, where did it come from? Well, we have two possibilities, but we're always going to take the positive one. And so we have that type of thing. The reason why the square root of 4 is 2 is because 2 squared equals 4. So in other words, we plugged in 2 into G and out popped a 4. Therefore, when we pull him back, right, we're coming back this way, he comes back to +2. Okay, now, this says you plugged some number into this function right here, and out came a -4. And now we're asking, what number was your input? Well, that's impossible, right? There's no way that you took some real number here, plugged it into x squared, and got a negative number. Does it make sense that that doesn't make sense? Right? Like we're saying, like if you were to say, okay, the square root of 4, you think, oh, you took a number, you multiplied it by itself, and out popped a +4. Okay, I know that. Why? Because 4 is equal to 2 times itself. Good. Okay, great. No problem. That's the number that came out. But when you say -4, that means you took some number, we don't know what it is, and when you multiplied that number by itself, you got a negative number. No, you didn't. That did not happen. There are no real numbers that make that true. There are imaginary numbers that make it true, but we're not there yet. We're getting there soon. As of right now, when we're dealing with these functions right here, we can never plug in anything less than 0. 0 is perfectly fine. What's the square root of 0?
0.
0. Why? Because 0 times 0 is 0. It is a perfectly good output. And we could say, yep, if 0 was your output from this function, your input must have been 0. Perfectly fine. But if you're trying to plug in a negative number here, you're in effect saying you took some number, you squared it, and out came a negative number. No, that never happened. So we would say the domain of this function f, that as I've written it right here, the domain of f is going to be, x is going to have to be 0 or bigger, which we could write as, since we can include, let's visualize where this is on the number line. And it's, oh, hey, look, it's right here, actually. Is 0 allowed?
Yes.
So we're going to include 0. And is every positive number perfectly good?
Yes.
It is. So what is the domain here?
X. Well, aren't
As an
any
interval. How would you write this as an interval?
aren't any negative numbers allowed too? Oh, wait.
X squared. We're not talking about this guy. We're talking about the square root now. Remember, the square root, what goes in here, whatever goes into a square root, it must be the case that that thing is positive or equal to 0.
Right.
So if x is the thing that goes in, it must be the case that x is bigger than or equal to 0.
Mm-hmm.
And so let's forget about this picture for right now. And we're just going to say, okay, then the domain of this guy, we're saying it can be 0. We're including 0, and it could be anything bigger. That's perfectly fine, right? I could plug in a 4. I could plug in an 8. I could plug in a 16. Those are all good. But I can't plug in a -1. I can't plug in a -2. They have to be these numbers here. So
Okay.
I can include 0. 0 is included. So I'm going to do like that right there. And we're going to say all of these guys. So how do we write that domain right now?
So you have the X thing and then the E symbol, right?
No, that would be if, well, yeah.
Or are you doing the
Yeah, like, but what I'm doing, I'm just saying, what's the set?
okay?
So it should be this. The closed interval, well, the half closed interval, including 0.
So that's what I was gonna say, but can you also include the X with the E sign or no?
Well, that's if we're talking about an X. Like you could, but remember how I defined this function, domain of. All we want to know is the set.
Okay.
So you could now, so here's a few things you could say. You could say this where X is in this, right? So you could say this right here, and therefore X is in one of these, then you're fine. But when I'm asking for the domain, I'm not really looking for this thing right here. I'm just saying, what is the set? That is the set itself.
Okay.
Let me think. Another thing we could do is we could say this right here means the same thing as the set of, to make things less confusing, I'm not going to use X, I'm going to say Y. The set of Y such that 0 is less than or equal to Y. If you think back to quiz 0, this was all part of that. Like, how do we go between these guys right here? That means the same thing as that. Yeah, and if you want to do that, okay, that's cool. Now you even could say, yeah, it's the Y in this set, but that itself isn't really a, this would be like, if I were to ask something like, what values of Y solve this equation or something like that, then we'd be looking for something like this. But if we're just talking about the set, and whenever we're talking about domain and range, we're only talking about the set itself. And that's kind of nice because it doesn't matter if there's an X in there or a Y or a Z in there. It doesn't matter what that thing is named. This is always true. It's always the case that the inputs to this guy are in this set right here.
Okay.
So yeah, it's subtle, weird little differences and stuff like that. So okay, so there's that. And finally, one thing that we're going to have to do is this. Suppose, so we're going to have to do two more things. Suppose I give you this function right here. What is the domain of F? So this is how I would think about this. I would look at this and say, okay, domain of F. What are my possible problems here? Well, I have a square root. I know that that inside a square root, whatever I put inside a square root, whatever that thing is, that thing has to be bigger than or equal to 0. And that makes sense, right? Like you can't plug in negative numbers. You could plug in a 0, that's fine. Any positive number is fine. So this is kind of what goes through my head. I say, well, I have a square root. So I have to do this thing. I have to see whatever that stuff is in the square root, that stuff must be bigger than or equal to 0. So then I just ask myself, okay, well, what's that stuff? In this case, it's x plus 1. Okay, so that's just x plus 1. This says that x plus 1 has to be bigger than or equal to 0. So then I'd say, well, let's get the x by itself. Now, this should harken back to the very beginning of this class, right? Like, how do we write this in interval notation? Well, the set of x, the set of input values where this is true, I would say subtract 1 from both sides. So I'd say, okay, x has to be bigger than or equal to -1. What does that look like on the number line? Well, we have infinity up here, negative infinity down here. There's a -1 right here. Now it has to be bigger or equal to. So I'm going to go ahead and say, here's this guy right here. We can include -1. And so here's my interval from -1 inclusive all the way up to infinity. And that would be my answer. -1 up to infinity. Soft bracket. And now let's just make sure that that works. Let's just make sure. This says that I can plug in a -1 and it makes sense. Let's see if that's true. F of -1 is equal to, wherever I see that, I replace it right there and I get a -1. So this says -1 plus 1. That is the square root of 0. I could take a square root of 0. No problems there. That's just 0. Okay, good. That endpoint looks fine. Can I plug in bigger numbers? Yeah, I could see that. As I plug in bigger numbers, that thing's always going to be positive. I'll be plugging in a positive number into a square root. Yeah. Perfectly good. No problems there. Okay. So that's the idea there. Anytime you have a square root in a function, you'd have to say, okay, that's good. Like that's one of the things that we have to consider when we're talking about domain and range and stuff like that. Now let's throw a curveball into the mix. Uh-oh. Now we have two problems. We might now, when I'm thinking about what's the domain of F, that's my question. Find the domain. I have two problems. One is the one we just discussed, which was the square root. But there's another problem. What value can we not have here?
1.
You cannot plug in a 1 because here we have two problems. We have the division by 0, which we cannot have, and we have the no negative square roots, or no negs in roots. In even numbered roots, right? Any even number of roots. So the division by 0, it has to be the case that x minus 1 is not equal to 0, which, like you just said, x cannot equal 1. This one we've already done. We said that whatever goes into the root has to be bigger than or equal to 0. So that means x has to be bigger than that. So I'm just going to think about, in this case, I have an interval, and we've already done that interval. We know it goes from -1 up to infinity. So that's the restriction I have from this part of it. But now I have an added restriction. It can't be 1 as well. So I'm going to have to pull out a 1 right here. When I do that, it's going to give me intervals like that and like that. And so finally, for my domain, I have to combine these two answers and say, okay, it has to be this guy right here. It would have to be from -1 inclusive up to 1, soft bracket, union, soft bracket, 1 up to infinity. And that should take care of everything. Everything in that interval gives me a positive number or a 0 up here, which is good. And it misses the number that gives me a division by 0 right there. Okay. Almost done. Does that make sense? You following me there? I can't hear you. You good? Are we frozen? Oh, you might be a little.
Are we good?
I think we're good. I can hear you again.
Okay,
So making sense? We just basically, we're looking for any function that we're given. We're trying to find now two things. It's not just division by 0 that could screw us up. Now even number roots have to play along. So, okay. One last question before we go. What's the domain of this? Are you frozen?
No.
Okay. Do we have any problems? Well, first off, 0, there's no problem there, right? Kind of by analogy, there's no problems with the positive numbers, right? I mean, are there any problems with cube roots of negative numbers?
Yes.
What?
No.
No. Because think about it. Earlier we did something like this. What was the cube root of -8?
2 -2.
-2, right? Because why? Well, because -2 cubed is equal to -8. And so the idea here is with an odd number root, we don't have to worry about the restriction. It's perfectly fine to say, plug in a negative number, because with the cube root, if this is x cubed, just like we were talking about earlier, it actually makes sense to say, hey, you took some number and cubed it, and out came a -8. Where did it come from? Well, that was actually pretty easy to figure out. You figured it out, right? -2, because when you cube -2, you get out a -8. So we have no problems with negative numbers going in here. Ditto with any odd power, right? So to kind of sum this up, so the answer to this, the domain of f, in this case, the domain of f was all real numbers, everything from -infinity to infinity, no problem there. And so what I'm going to do, try to generalize this a little bit. So when you have, let's do this one to be even. When you have an even root versus an odd root. The domain of an even, in other words, the thing that goes into here, we can only plug in numbers from 0 up to infinity. we cannot plug in negative numbers into here. 0 is perfectly fine. Whenever you have even root, plug in a 0, that's perfectly fine. With odd roots, there are no problems. Every real number will work just fine. So when you have an odd root, the thing that goes into it, there's no restriction on odd roots. And that's because you get every number out with an odd root, right? Like -8. -8's a perfectly good output. With even roots, though, that doesn't work, right? Like x to the 4th equals -5. Well, no, you can't take a number, raise it to an even power, and get out a negative number. That does not work. There's no number that makes that work. So that's why we have to restrict the domain here and say from 0 up to infinity, we can include 0, but here with odd roots, no restriction at all. That's the last thing you need for your homework, I believe. And yes, that's it. Any questions?
Okay. No.
Okay. Okay. And
Not
if you
yet.
have any questions as you move along, or if there's something that I've forgotten to cover, please text me, let me know. So here comes homework. Oh, buddy. Oh, buddy. So homework. Chapter 7, section 1, pages 295 to 296. We're gonna do it all. 1, 2.
No.
1 through 53 odd.